This is 8.2, or sorry, 8.1, part 2 for Math 31. And in part 1, we looked at kind of, several different exponential functions to basically get to the summary of the investigation. And really what it is looking at the value of the limit. And I'm going to draw what these look like if the base, now keep in mind when they talk about the base, they're talking about y equals b to the power of x in this context. And if b is greater than 0 but less than 1, it's exponential decay. If b is greater than 1, it's exponential growth. Now, we are not going to talk about what happens when b is negative because that graph would only exist at very discrete x values. But if we look at this graph, when b is in between 0 and 1, this is why we can make these limit statements, is that as x approaches negative infinity, so that's as the graph moves to the left, the graph is approaching infinity, right? It's getting larger and larger. But to the right, as x approaches positive infinity, that graph is approaching 0. And basically the opposite happens for the other. And the bottom line is that if I take the number 1/2 and put it to the power of x, as x gets larger and larger, I'm continually halving and halving and halving until eventually the remaining amount is so small that you can't half it ever again. Now, if you are willing to go to a couple thousand decimal places, it never actually becomes 0. And that's that important bridge between the 30-1 math and the calculus, is the concept of those infinitesimals. It gets so large. Infinity is not a number. It's the concept that if we let it run forever, eventually it will approach 0, or become 0 is maybe not the terminology, but it is the idea, that limit, that this function is getting closer and closer to the horizontal asymptote at 0, but never actually equaling 0 at a real number. All right, the reverse is true over here. So if we look at the second graph, and I'll put an asterisk there, that as x approaches negative infinity, that's to the left here, the value of the function is 0. And as we approach positive infinity, the value of the function would go to positive infinity. It gets larger and larger and larger, basically without bound. Now, what we can use then is that knowledge to talk about some maybe basic exponential functions. So it wants us to relate these to y equals 2 to the power of x. And I really do think that we should talk about the function transformations. If you compare this graph to y equals 2 to the power of x, then what we have to do is horizontally translate it 4 to the right and vertically translate it 3 up. Now, if you're struggling with that 3 up, then it's probably beneficial to rewrite this function as y equals 2 to the power of x minus 4 plus 3. And it's a little bit easier, I think, to see that we've added 3 to that function. Now, what I'm going to do is I'm just going to kind of draw a dotted line. And I'm going to talk about how this is y equals 2 to the power of x. And if I wanted to draw what my new function would look like, what I like to do is immediately draw where my asymptotes would be. Now, there's only one asymptote here. This black dotted line has an asymptote at y equals 0, right here, that little red line right there. Now, if I move that 3 units up, it becomes a horizontal asymptote at y equals positive 3. And then when I move it 4 to the right, basically what that means is that the graph is going to open or increase a little bit later, and it's going to look something like that, give or take. Now, this is a sketch. You have your calculator for a particular, kind of more exact graph. One of the more important considerations here, though, is that using this graph, I'm going to do the second example kind of, well, no, I'll write it down, and then I'll probably just go back to this graph in a second there. Okay, for B, students struggle with where that negative actually is. I would recommend that you write it like this, as -1 times 2 to the power of x plus 1. And that's really important because it is not a negative base. You will not have to deal with negative bases. So similar to the last one, I'm going to picture that y equals 2 to the power of x in black here. And then what we can talk about is that if I want to get to this graph from y equals 2 to the power of x, then I need to reflect over the x-axis. That's that -1 in front. And then what I'm going to do, over x-axis, spelled that wrong, is I'm going to horizontally translate it 1 unit to the left. So we start to see some of the information that we picked up in Math 30-1 kind of creep into calculus a little bit, and what this would look like, because I'm not moving it up and down, it still has the horizontal asymptote at y equals 0, but now what it looks like is something like this. All right, so not only is it now opening downwards, but it also has been moved 1 to the left, so it's going to open downwards kind of sooner, if we want to use that language. To really get into these graphs, you would need to use your calculator and maybe set up a table of values to look at some of these numbers. But we can use that information to talk about what happens as x goes to infinity. So I'm going to write this out, that we're going to look at the limit as x approaches infinity of the first function. So that's 3 plus 2 to the power of x minus 4. And then we're going to look at the limit as x approaches negative infinity for that function. Again, 3 plus 2 to the power of x minus 4. On the other side, I'm going to do it in a different color, is we're going to look at the limit as x approaches infinity of negative 1 times 2 to the power of x plus 1. And then the limit as x approaches negative infinity of negative 1 times 2 to the power of x plus 1. All right, now the best way to deal with these limits is using a little bit of our limit knowledge. I'm going to turn this into two limits. The limit as x approaches infinity of the first term plus the limit as x approaches infinity of the second term. Now, if you were to look at the graph of 2 to the power of x minus 4, it is exponential growth, so it gets larger and larger and larger. Now, the limit as x approaches infinity of 3 is 3, but the limit as x approaches infinity of 2 to the power of x minus 4 is infinity. Well, 3 plus infinity is effectively, if you spit in the ocean, do you raise the level? No, right? You've added a minuscule amount of water to an infinite amount of water, so we would say that that limit is equal to infinity. Now, as we approach negative infinity, we're going to do the same thing. So as x approaches negative infinity of 3 plus the limit as x approaches, negative infinity of 2 to the power of x minus 4, this is still 3. It's the limit of a constant. But if we look at the graph of 2 to the power of x minus 4, as x approaches negative infinity, that approaches 0. And 3 plus 0 is 3. And I'd like to point out that that is where the horizontal asymptote plays a part, right? Okay, for the other side here, that negative 1 certainly does matter. It's multiplied onto this. I'm going to write underneath that this becomes the limit as x approaches negative 1 of, the limit as x approaches infinity of negative 1 times the limit as x approaches infinity of 2 to the power of x plus 1. This is negative 1. This is infinity. So the value is negative infinity. Take another look at that graph and see if that's true. As x increases to the right, what happens to the value of y? And you'll see that it goes to negative infinity. Down here, this is the limit as x approaches negative infinity of negative 1, little extra bracket there, sorry, times the limit as x approaches negative infinity of 2 to the power of x plus 1. This is negative 1, but this is 0. Anything times 0 is 0, so that limit is equal to 0. And yet again, I want to talk about how that's the horizontal asymptote. It can really, really help when you're taking the limits of these exponentials to look at their graphs, right? Visualizing what the limit's actually saying is a pretty important concept in calculus. All right, one last example. It wants us to use the graph of y equals 10 to the power of x to sketch the graph of y equals 10 to the power of x minus 1 and then minus 2. So just so we can see it, y equals 10 to the power of x looks like this. It does change very, very quickly. I'm just going to grab a couple points off there. 0, 1 would be there, and somewhere over here would be 1, 10. Oops. And if we really want another point, we could certainly grab this point, which is at negative 1, 1/10. Those are all valid points. To go from y equals 10 to the x to this graph, this is that Math 30-1 knowledge that that's a horizontal translation 1 to the right and a vertical translation 2 down. Now, the vertical translation is important because what it does is it shifts our horizontal asymptote to now be at y equals negative 2. That horizontal translation 1 to the right isn't as important. It really just means that 0, 1 doesn't just become 0, negative 2. There's more to that because it moved to the right as well. And then what my graph would look like is roughly something like this. Again, not too worried. It is just a sketch. The bottom part is what's much, much more important. Being able to go from a function to talk about the asymptotes, domain, and range, and so on, the graph is useful for that. We're going to make sure we can see it at the same time because the asymptotes is pretty easy. There is no vertical asymptote. We'll write that down. It does not exist. But the horizontal asymptote is at y equals negative 2. For the domain and the range, the domain is that x is an element to the real. All right, x can be anything. There's no limit on the value of x. But what about y? If you look at y, because this is exponential growth, it's always greater than the asymptote. The asymptote, though, now is at y equals negative 2. So we would have to say that y is greater than negative 2, but it's any real number that satisfies that restriction. All right, not too bad, I hope. Take another look back. If you've kept your Chapter 7 materials, good on you. Take a look at that 30-1 material. If not, might not be a bad idea to take half an hour and go, watch a couple videos about exponential functions and how to transform them. That's all on my YouTube channel. You just have to look for the Math 30-1 Chapter 7 playlist.